artist. So I apologize right at the beginning that my shapes may not be perfect, but then I looked up the textbook and theirs wasn't perfect either. So evidently everybody has a problem on trying to do a 3D thing on 2D paper, right? Maybe one day when we get holographic projections, we can actually see the thing in 3D and look at it in 3D. But essentially, we're going to look at a final different way of describing locations on a surface. We've done X, Y, Z, you know, things like, you know, Z equals X cubed plus sine NY, that kind of thing. And we've done polar, right? But that's really for 2D, but we've done cylindrical, which is for 3D, and cylindrical is very like polar, right? R, theta, and Z. And now we're going to do spherical. And spherical coordinate system uses 3 numbers to represent a point in 3D space. And I want you to imagine that the tip of this pen is the point that you're interested in, right? So it's like that red line there. And we're interested in telling people where P is. And they do it by 3 numbers. The first one looks like a kind of lopsided P, and it's the Greek letter RHO, which you pronounce as rho. In some textbooks, they're going to call that little r. But since this textbook is using rho, I think it's just makes more sense to stick to that letter. Then we have 2 other ones. Rho, by the way, is the distance from the origin to that point P. So you can understand why it might be called r, right? Distance from the center. The other 2 angles are phi and theta. Phi looks like that. PHI, pronounced as phi, in the same way you pronounce phone. It's got that sound in it. And theta is the angle that you make there. So you imagine you wanted to do P, you'd start off at the origin and you'd have like a pen that can move, rho units long. And then on the floor, you would rotate it maybe 30 degrees, and then you'd bevel it up, right? But actually you measure the angle from Z downwards. I guess that's a little bit weird, but that's how you measure it to get the guy phi. So these 3 numbers will tell you any point in 3D space. Now let's tell you a little bit about the range. Rho can be any positive number. So we don't talk about rho being -4. Doesn't make sense because it's a distance. The angle theta only takes values typically from 0 to 2 pi. You don't need any more because that basically covers the floor. And the angle phi isn't 0 to 2 pi. It's only 0 to pi. 0 would be the z-axis positive. Then if you rotate it, pi upon 2, pi. Now you might think, well, that's only going to get all the points this side. But remember, theta can be on the floor. So can't you rotate theta and then phi only needs to come down this way? So that is basically every point in the 3D universe. You only need those numbers, and the only one of them that actually takes on an infinite value is rho, which is basically how far away from the Earth are you, if you're thinking in space terms. Are we good with that naming system for how a point in 3D space can be described by rho, phi, and theta? So far, so good. Okay. Now I better get all my other notes put to the side here because
is this going to turn into vector fields?
We don't. I mean, anything can be turned into a vector field, but the vector fields that we're going to deal with are X, Y's, and Z's. But I mean, you can turn a vector field that uses X, Y's, and Z's into spherical coordinates. The way that you do it is basically using this. X can be turned into rho, sine phi, cosine theta, and you can look at the textbook and it proves it to you. The y coordinate in terms of those is called rho, sine phi, sine theta, and the z coordinate is rho, cosine phi. That's just something you write down on a card and keep it handy for this section. Okay. Now, do you know how you do a triple integral dv? You know, dv is dx dy by dz in any combination. What does that look like then when you take a triple integral that has x, y, z's into it and you rewrite it in spherical coordinates? Well, you get a rho squared sine of phi, d rho d phi d theta. Now, analogy. Remember when you did cylindrical, you get an extra r dr d theta thing? Remember that one? An r. Well, you see this time you get a lot more for your money. And the next section after this one is change in variable. And we will be able to show you the cylindrical one. I don't think I'll show you the, well, I might tell you how to get this one, but it's much uglier. So let's talk about solids, surfaces of solids in 3D space. And apologize for not making that clear, that's a 5. Suppose you wanted to describe to me a sphere of radius 5. So suppose the region E was basically a solid sphere. How would you describe that? Well, the radius is 5, rho goes from 0 to 5. Since it's the entire sphere, 0 to pi, 0 to 2 pi. So that would be like in 3D space, an entire sphere. Now, if you talk about a hemisphere is the top half, well, could be any half, but typically the top half of a sphere. And do you notice what the difference is? Right, these are the limits of integration if your solid was a sphere. This is your limit of integration if your solid was the top half of the sphere. What is the difference between those two? Because there is one.
The phi value is half.
Yeah. Now, if phi starts at the z-axis, can you see if you only go to half phi, won't that rotation with the other guy generate the top half of your circle? If you wanted the bottom half of a hemisphere, wouldn't you do pi upon 2 to pi? That's all you would do. Now, if you want something in the first octant, this guy here, rho is still 0 to 5. In the first octant, since it's a positive x, positive y, positive z, the first octant has a phi between 0 and pi upon 2, and so does it also have a theta from 0 to pi upon 2. So cylindrical or spherical coordinates, I should say, are typically used when the solid that you're integrating in, right, your triple integral with a solid, it's a sphere or a bit of a sphere. And occasionally, just occasionally, a cone as well. Cones are a bit messy, but they do exist. Oops, got some of my notes. There we go. So I'm now going to show you. It's the best I could do, which is why. Oh, Terence, you have a question?
Yeah, in that last section, you had a bunch of dots in the F equals.
Yeah. Well,
what do those stand for?
The X, Y, and Z would be replaced by rho, sine, phi, cos theta, all those variables at the top. So I didn't have enough room and I didn't want to write them. So I'll show you what I'm getting at. This X, Y, and Z, these dots, the X would get replaced by this ugly guy, the Y would get replaced by this ugly guy, and the Z would get replaced by that. So you can imagine the first 3 dots would be him, the next 3 dots would be him, and the last 3 dots would be him. But if I wrote that, it would be over here.
Thank you.
So let's go. I've got a guy that I've just found, took me a little bit longer than I thought to set it up, which is how do you sketch things, surfaces, and basically this thing inside the surface, which is a solid, using GeoGebra. So here we go. Make this a bit bigger, I think. Now, they had to do a kind of workaround. There might be a spherical drawing piece of software out there. I just haven't managed to find it right now. So you try to, if you can, you try and write your equation as rho equals some function of phi and theta. So for instance, if I go here and I just say the sine of x, and I know it's x and y, but that's just the workaround. X in fact is theta and y is phi. So this would be this rho equals the sine of theta cosine of phi, right? And zoom in that shape. There we go. And rotate it. That's kind of pretty, isn't it? It's got a top and a bottom half to it. Now, if you move this guy around, you see you can undo some of the shape. So if you only choose to use one of your angles, your theta, you know, from 0 to 180, you see you only get the top half, and if you go to 360, you get the whole lot. If you move this one around, you see that you cut it off in a different way. I'll leave it at that. There, do you see I've kind of lopped off a piece of the shape there? How about x add y? So this would be theta plus phi. Don't know what that's doing there. We don't have it. There we go. What's x plus y going to look like? Should be fine. Like, done it. I've lost my guy. Oh, here it is. There we go. I just had to scroll out far enough. That's quite an interesting shape. There we go. Isn't it like a spiral staircase? Right. So if you want it,
also kind of like a seashell.
Yes, a lot of them. If you look at this one as a surface, can you see? Do you know, if I was one of those stupid architects who build things because they look pretty, but are downright impossible to live in, you know, the kind of buildings? One of them's probably going to build a stairway that looks just like that shape. I mean, it looks really cool, but it'd be impossible to use. Yeah, you're right. You do get shapes that look like, well, let's open this up to its full capacity. Yeah. There we go. I don't know what you'd call it. It's kind of helixy shape. Okay, spent enough time. For those who like to see things, there's a piece of software there that's called something like Spherical, and you can play about with it. So let's return back to the math of it. Yes.
Did that that shape you showed us actually have the Fibonacci sequence in it, or did it just look like the Fibonacci sequence because of the spherical shape?
Short answer is I don't know. It might have. I couldn't tell by looking. I mean, you can get helixes generated without Fibonacci. I mean, you can do a helix and a spiral in 3D, just the space curve, by just doing a version of 2 cos theta, 2 sin theta, and t. That would do it. And that has nothing to do with Fibonacci.
Speaking of Fibonacci, did you hear the joke about Fibonacci?
Yes, I think you told us. It wasn't as good as the other two.
It's worse than the last two jokes combined.
I gotcha. The last two combined. I forgot that piece of the thing. Right. So let's jump right into, what do these questions look like? Well, the first one is that we're going to try and rewrite equations that are surfaces in X, Y, Z, and rewrite them in terms of, if we can at least, a simplified version of spherical. And to be able to do that, you have this. But there are some shortcuts. it's not uncommon for a lot of equations to have versions. I'm not sure what I'm writing here. I don't know what you can see. Right, there we are. Can you see this now? Right, okay. What do you think x squared plus y plus z squared comes to? It's equal to something. In terms of either rho, phi, or theta. What's x squared plus y squared plus z squared going to get you?
Rho.
Right, just rho? A little bit more?
Well, we've got 3 cosines and
Don't need to do the algebra, although that would eventually get it. Isn't x squared plus y squared equals r squared? Don't we use that a lot? Well, in 3D, x squared plus y squared plus r squared equals rho squared. So it's a useful thing because can you imagine there are going to be a lot of questions? And here's my first one, where you're being asked to take a surface, in this case, x squared plus y squared plus z squared equals 9, and convert that into spherical. Well, that guy is r squared equals 9. And that means r is the square root of 9. And since r has to be, sorry, rho, but r is another name for it. Rho squared is 9. Won't rho just be 3 because you can't get negative 3s? So if you took all the points in 3-dimensional space that had the property that the rho value was 3, you'd end up with the surface of a sphere. Yes, Tim?
Are these questions on the homework?
This one is question 1A.
The homework doesn't show up, at least for me.
Oh, okay.
I mean, I prefer to not have homework, but
I've not got time right now, but when this lesson's finished, I'll go back in. I probably didn't check it to let you see it, but this is what it is when you see it. The second one, you don't expect great things. In a way, this is more realistic. You might get a surface that looks like that, and you're going to turn it into spherical. All that means is substitute x, y, and z, and try your best to make it look pretty. This one, we did a shortcut. But if you'd replace the x with this, the y with this, and the z with this, can you trust me, about 6 lines later, you'd end up with that, right? This one, there are no shortcuts. So x is going to be rho sine phi cosine of theta squared. Oops, there we go. Take away rho sine phi sine theta squared. Of course, not enough room. Take away rho cosine phi squared, and the whole thing's going to equal 1. Right, if you take that guy, you got a square, you got a square, you got a square. Take away this guy, you got a square, you got a square, you get a square. Take away this guy, what you're going to get? You're going to get a square, you're going to get a square, and you're going to get a 1. And your job now is style points. That is, try and make this thing as pretty as it can be. And I'm looking at this, and the only thing I can see right now is, would you agree that everybody contains a rho squared? So I'm going to pull that out as a common factor. And don't worry about the 1, we'll never be able to fix that. Now, it's not that common, but sometimes you have to do it. That only 2 of the terms share a common factor. And do you notice these 2 terms can share a sine squared, phi? And the reason why I'm going to do that is that I can at least make these guys a little bit nicer. So I'm only pulling out a common factor from the first two. Okay, get the cobwebs dusted off. Sine squared theta or cos squared theta, take away sine squared theta. It's not 1, but what is it equal to?
Wouldn't it be when you factored it out, wouldn't it be the sine squared of rho?
No, because it's not got, no, short answer.
I
Cos
like
squared
it
theta.
with I'm talking about the I forgot what Greek letter it was.
Are we good,
The
Sally?
little loopy one.
Sine squared phi.
That's what I
Oh
meant.
yeah, I forgot that. I agree with you now. But what's cos squared take away sine squared theta? That is equal to something, which is what I was trying to get.
Cosine of 2 theta.
That's it. And then you get to the point where, yeah, that's the end of the line. So that horrible mess is this guy turned into spherical coordinates. And why do you need to do that? Well, forget the one, but this expression here might be the guy that ends up there. Right? Because when you're doing a converting a triple integral from x, y, z to spherical, don't you have to convert everything, all the x's, all the y's, all the z's? So this here might have been one of the functions.
Wouldn't we be able to simplify that with the cosine squared theta being 1/2? No, wait, never mind.
Right.
The cosine 2 theta over.
Gotcha. Right. Question 2. Yeah, sometimes I have to say things before I change my mind. I have x squared. Right, I have x squared plus y squared plus z squared equals 6z. And I have a cone, which if you don't know what a cone looks like, it looks like that guy. And we're told that it's inside the sphere. And we're told that it's outside the cone. Now, can you imagine that's a sphere and this is a cone? And so we're talking about the solid, which is basically all the stuff. Oh, you can't draw them. I'm going to give up trying to draw these things. I can visualize it. Can you imagine a sphere and somebody's bore a cone hole inside it? The solid that we're talking about in this story is not the hole, which is the cone, but the bit that's left over, right? The bit that's still uncut, right? This bit here, all the way around the shape. And we are going to try and create, hopefully, what the limits of integration would be for this region. Okay. So in this case, we need to try and, they're not bothering about the theta, but by the way, I can tell you what theta is going to be. In this solid, based on the fact that it's really just a sphere with some of it missing, what will the theta be for every sphere if it's a whole sphere? Because it's the same start and finish value.
0 to 2 pi.
Right. As long as it's a whole sphere that's had bits cut out of it, that's true. They only want us to find the range in rho and the range in phi. Okay. So I'll put this over here. I'll start with the first one. X squared plus y squared plus z squared equals 6z. And I'm going to get out of this values for rho. Well, I know what x squared plus y squared plus z squared, isn't that just rho squared? 6z, I'll have to go over here and write down 6 rho cosine, oops, there we go, cosine phi. Then I get rho squared, take away 6 rho cosine phi equals 0. I'll then pull out rho as a common factor. And that gives me 2 values of rho. Are we comfortable so far? And guess what? I now know the start and finish value of rho, right? Right, rho goes from being 0 up to 6 cosine theta. This is the only correct version of that. What is wrong with doing it that way? Because in some situations you could switch the angles, right? It could be, you know, A, B, or BA, right? Could be either way around. Why is that impossible?
Rho can't be negative.
Right. That's why there's only one right way to do it, right? Well, what else have we got? Well, we have a Z thing going on, don't we? And Z is equal to the square root of x squared plus y squared. And I just realized because it takes so much room, I should start on a new piece of paper, so I will. Let's see what we get out of that guy. Well, it's going to be the square root of rho. I have to make sure I write this cos theta squared plus rho sine of phi sine theta all squared. What's that going to get me? That's going to get me rho squared sine squared of phi cosine squared theta plus rho squared sine squared of phi sine squared theta. And what do I know about Z? Z is rho cos theta. Rho cos phi, I should say. Okay. I can pull out a rho squared. I can pull out a sine of phi. And if I do that, I get a cos squared theta plus sine squared theta. Agreed? Okay. Square root gets you a rho. That guy gets you this fella. And this guy gets you 1. Are you comfortable with rho sine phi? Okay. Now, if I divide this, or if I divide both sides by rho cos phi, don't I get 1 is equal to tan of phi? Oh, by the way, I'm looking for a range of phi here, right? I already know what theta is. I know what rho is. What does this guy get me?
Is it inverse tan of 1 equals phi?
And what is the, what angle is inverse tan of 1? You're right, Tessa.
I don't know. Sorry.
What angle has a tangent of 1? That's another way of phrasing it. Yeah, pi upon 4.
Is it pi over?
4, yes. You've paused on this, so I'm assuming that our Visio has locked out. Now, this fella is described as being outside the cone. So you can imagine the cone was like this. And so that pi upon 4 is one of the numbers. But since you're outside the cone, the other number is pi upon 2. And that's because of, if you look up the description of what a cone looks like, the range of the angles only goes as far as pi upon 2, because after that it stops being a cone. Can you imagine starting at 0 and finishing at vertical, right? You can't get any more than an angle of pi upon 2. Phi is measuring essentially the angle theta here. I should say phi there. It's measuring an angle. So there's a limited number. So we got the guy. So it's messy.
Excuse me, where
Yes.
can I go to look at that information that let you
You
know
get
that?
you get it in ebook. Go into your ebook, look up section. What's this called? Chapter 15, whatever this one is. I'm written it down in here. Have I? I have. No, I haven't. It's chapter 15, 7, 8, 9, whatever the number is, but it'll be called spherical coordinates, and it'll tell you the equation of a cone and the restrictions on it.
I think it's 15.8.
15.8, I've just been told.
Thank you.
Right. Well, that's kind of the warm-up. So we need to do some integrals, don't we? Triple integrals. And the first one we're going to do is one where everything has been given to it. So we're going to find rho squared sine of phi d rho d theta d phi. And that has a rho going from 0 to 1. This has got a, make sure it's theta, second there. This is going from theta equals 0 to pi upon 2. And this is going from phi equals 0 to phi equals pi upon 6. Really, you don't need to know spherical coordinates to do this. Couldn't they just call these guys X, Y, Z, and you'd have the same kind of question? So first thing, to make life easy, is this separable? Could I break this integral into single integrals multiplied together? Now, isn't the clue here that these are all numbers?
Yeah.
Right? And isn't the second clue that this is made up of separate factors? So if I was going to do that, I would do phi equals 0 to phi equals pi upon 6, and the guy that's got a phi in it is him. If I'm doing theta, theta goes from 0 to theta equals pi upon 2 in this question. Okay, this has happened before. What did I put here where my finger is for an integral where there's no sign of theta? Because something has to be written there, right?
1.
You just think, right? 1. And lastly, a rho equals 0 to a rho equals 1 of rho squared d rho. Can I dot that guy? Are you comfortable? You could integrate each 3 pieces and multiply the answers, and you're going to have to know the pi upon 6, right? You're going to have to know the cosine of pi upon 6. Does anybody know what the cosine of pi upon 6 is?
Actually, it would be the negative cosine.
Correct. What is the negative of the cosine of pi upon 6?
Negative root 3 over 2.
Yes. Okay, so you might want your unit circles kind of handy. I believe, I'm looking at this question here, I believe they give you a choice of solid. So if you go to my, well, you can't really even use that, sorry. Okay, there are 4 solids there. One of them is going to be the right shape. I guess you're going to have to figure it out. Okay. I'm only going to set up the limit of integration for this one. It's a triple integral of a ball, there's a new letter, of x squared plus y squared plus z squared squared dv. And the ball that they're talking about is a sphere of radius 3. So I'm going to go in no particular order. The limits of integration for a sphere of radius 3. Rho is going to go from 0 to 3. Okay, what is for a normal sphere, right? Not a semi-sphere, half a sphere, or any other kind of sphere, but just a complete sphere. What is the range of values for theta?
0 to 2 pi.
Okay, and what is the range of values for phi? And it's not 0 to 2 pi.
0 to pi.
Are we comfortable with that's the standard guys you do for
He
a full sphere?
speaks about the same time my brain registers that my finger should start moving.
What, I missed that, Brendan. What were you saying?
I'm sorry, I was just talking to myself.
Oh, I think that's a good thing to do because I do that a lot, and it's the only way.
Yeah,
I'm
it helps with
intelligent.
thought process.
It does. Everybody is a bit of a thing. I'm mostly a visual learner. I can see things really well in my brain, but I like talking things through. So when I was grading your tests, apart from the occasional swear when someone done something really stupid and I knew that they knew what they were doing and it just frustrated me, I talk a lot. So if you ever walk by my office, you'll hear me talking about it. Well, this goes here and then that goes there, and then you take a square. Oh, I see what she's doing, and blah blah blah. You do what you do, right? I need a DV guy, don't we? Oh, this will be a great memory. Can anybody remember? And I've got it here to show you. Right? Hopefully you didn't catch it. They can go in any order you like. What goes here?
Rho squared sine phi.
You got it, right? Rho squared sine phi goes there. We're just getting all the basic building blocks. I might as well finish this guy off. You know that this expression is going to have to be turned into spherical. Actually, this one's a baby one, would you agree? Okay, just to remind you, isn't x squared plus y squared plus rho squared, z squared, rho squared? So doesn't that just get you rho to the 4? Right, you put the package together, and in any order you like, I might as well do it now. Rho equals 0 to 3. Theta equals 0 to 2 pi. And phi equals 0 to pi. And this fella becomes rho to the 4. And then you add in another rho squared sine phi. And then in the order I've written it, it's going to be phi, then theta, then rho. Would you be comfortable about completing that question now that we've set it up? You'd end up with rho to the 6, but aren't they variable separable again, which kind of makes your life a lot simpler? Got time maybe for one last one? Okay. We're doing a triple integral of a guy called E, for no particular reason, I guess. X squared plus y squared dv. And E is inside one sphere and outside the other. So can you imagine someone made a hollow ball bearing where the inside radius was 3 and the outside radius was 4? Would you agree that's what that would be? Inside one, outside the other. So I need a rho, I need a theta, and I need a phi. It's still a complete sphere, right? It's just got bits taken out of it. And because it's a complete sphere, aren't these two guys going to be what they always are, right? What's the range in rows based on this story?
It would be 0 to 4.
Agreed. And
I
dv,
said 0 to 4.
is it 0 to 4?
Because of that guy.
Yeah, so it's outside this one and inside that one, right? So it's 3 to 4. And dv then will be a rho squared sine phi in any order you like. And then you can do your guy. We'll have one more guy to do. I'll do it over here. Don't I still need to figure out what x squared plus y squared is, right? Great. And so x is going to be our rho squared sine of phi squared cos theta. And the y is going to be rho squared sine squared phi sine squared theta. If you pull out the rho squared sine squared bit, you've got a cos squared theta plus a sine squared theta, which gives you 1. And so you get rho squared sine squared phi. So it's going to be a rho squared sine squared phi, all of this, some more rho squareds, sine of phi's. I'm doing a d rho, d theta, d phi this time. The rho is going to go from 3 to 4. Theta is going to go from 0 to 2 pi. And phi is going to go from 0 to pi. Is this one variable separable?
No, I don't think so. Actually, wait, once you simplify everything. Yeah, it would be, wouldn't it?
It would be, yeah. So if we do the phi equals 0 to pi, we get, when you combine them all, you get a sine cubed of them. Theta goes from 0 to 2 pi, nothing there, so you get 1. And then you've got a rho equals 3 to a rho equals 4, of rho to the 4. Right. This is the only one I think is going to cause you some trouble, and it's sine cubed. Right, you're going to have to integrate sine cubed. Any suggestions for how you integrate sine cubed?
Would you split it into sine times sine squared?
Well, oh, yeah. If you mean by that 1 minus cos squared, I agree.
Yeah.
Yes. There's only one sine there, right? So it's a single sine and a 1 minus cos squared. What are you going to do next?
U sub.
And be careful, who is the u sub?
It would be cosine.
Just cosine, right? And off you go and you get what you get, right? And we go. Well, that's us for today. I think we learned some cool stuff. You learned, for instance, I cannot draw anything in 3D when it involves spheres. But good luck. If you can draw better, I want to see it. Right? So I'm just putting that out there. If any of you feel artistic and can draw in 3D, 2 things. Rosie, question. Oh, say your last name and bye-bye, and I'll hang about for questions. Rosie, you have a question.
Could you enable practice another on the homework?
Yes, I will also have to make it so you can see it. So I'll take a little note of both those things.
I can see my homework. I logged into
I can see it
WebAssign.
too.
Okay, then that's kind of done. You might just have to update your thing then. What we're looking for, Rosie, you want to, how do you phrase it again?
Enable
Try another.
practice another.
What's it called? Enable other, something like that.
It's
Practice
called
another.
practice another.
Practice. That's probably more like it.
Yeah, practice another where it generates the same problem but just with different numbers.
Gotcha. I'll stick that on my screen so I can see it.
So how does the mathematician get around on the beach?
I don't know how.
He rows his boat.
Oh, just because we got to row. Okay. Now, you know I'm calling this thing row, and some Americans going to say, no, we do not call it row. We call it row or something. I don't know what you call it. Have anyone heard the Greek letter rho before I mentioned it? So am I pronouncing it the way the Americans do?
Yes.
I pronounced it row, and actually the first time I heard the word, it's because there's a thing in a
video game called Horizon Zero Dawn, there's like a thing called a cauldron, and one of the cauldrons is called row.
So the guy
The-
has mathematical context. Tim,
The head of our engineering department also calls it row, but he was also one of your students.
have I been here that long that the head of things are now ex-students?